That faint hiss of static on an empty television channel is not just noise, it is the echo of creation itself. That signal is the cosmic microwave background, the oldest light in the universe. It is a baby picture of everything, taken when the cosmos was just an infant. By the end of this, you will know 50 astonishing secrets hidden within this ancient glow. This fossilized light holds clues to our cosmic beginning and hints at our ultimate fate. Why does this echo look almost perfectly smooth, and what do its tiny flaws reveal? What monumental discovery began with a struggle against pigeon droppings? The story of the universe is written in this whisper of static, and we are only just learning to read it. What does it mean to live inside an echo? That hiss is a perfect snapshot of the universe at 380,000 years old. This is the first thing you must understand. The cosmic microwave background is not random noise. It is a precise, full-sky map of the cosmos in its infancy, a photograph of the moment the universe became transparent. Before that instant, everything was a searing, opaque fog of plasma, so dense that light could not travel. As the universe expanded and cooled, electrons and protons finally combined to form neutral hydrogen atoms. In that moment, the fog lifted. The light that had been trapped, bouncing around for all those millennia, was suddenly set free. That first flash of liberated light is what we detect today, stretched and cooled by the expansion of space over billions of years into the microwave signal that fills the entire sky. We are living inside that flash. Every direction we look, we are seeing that same ancient wall of light, a fossilized moment from a time before stars, before galaxies, before anything we would recognize as structure. And the story of its discovery is as wonderfully human as the signal is cosmic. It began in the mid-1960s at Bell Labs in New Jersey, with two radio astronomers named Arno Penzias and Robert Wilson. They were not looking for the origin of the universe. They were simply trying to calibrate a giant, horn-shaped radio antenna for satellite communication experiments. But they kept picking up a persistent, uniform hiss that came from every direction, day and night. It would not go away. They checked every possible source of interference. They pointed the antenna at New York City, thinking it was radio pollution. The noise remained. They even suspected their equipment was faulty, and in a now legendary move, they meticulously cleaned out layers of what they described as white dielectric material from the antenna. In simpler terms, they spent weeks scraping out pigeon droppings, yet the mysterious hiss persisted. This was not pigeon interference. This was the echo of the Big Bang itself, a whisper from the dawn of time that had been traveling for over 13 billion years to reach their antenna in New Jersey. Their stubborn pursuit of a technical annoyance led directly to a Nobel Prize and fundamentally changed our understanding of everything. What they found was not a flaw in their machine, but the signature of the universe's birth. That persistent hiss Penzias and Wilson measured holds a precise temperature, a number that tells a profound story of cosmic cooling. The cosmic microwave background is not just old light, it is the coldest natural thing we have ever observed. Its temperature is an almost unimaginably frigid 2.725 Kelvin. To understand how cold that is, you need to know that Kelvin is the scale that starts at absolute zero, the point where all molecular motion theoretically stops. 2.725 degrees is just a whisper above that ultimate cold. For comparison, the empty void of deep space between galaxies, which feels unimaginably cold to us, is actually warmer. It sits at about 3 Kelvin, heated ever so slightly by the starlight of all the galaxies. The CMB is colder than the deepest, darkest vacuum you can conceive. This uniform, deep chill is not an accident. It is the direct and inevitable result of the universe stretching for 13.8 billion years. Think of that primordial light as a wave. When the universe expands, it stretches the wavelength of that light, just like pulling on a spring. A longer wavelength of light carries less energy, and lower energy means a lower temperature. The CMB has been cooling down steadily since that first flash, stretched and diluted by the expanding fabric of space itself. That precise number, 2.725 degrees, is one of the most important measurements in all of cosmology. It is the ultimate thermometer reading for the cosmos, a direct confirmation that the universe was once unimaginably hot and dense and has been expanding and cooling ever since. This uniform chill is the key signature of the Big Bang, a fossilized temperature that blankets the entire sky. This uniform chill is a photograph of a very specific cosmic birthday. The cosmic microwave background is a snapshot of the universe at just 380,000 years old. To grasp the significance of that moment, you have to step back and picture the scene. For those first hundreds of thousands of years, the entire cosmos was a searing, swirling fog. It was not made of gas as we know it, but of a plasma, a soup of fundamental particles. Protons and electrons, all with positive and negative charges, were constantly colliding and repelling each other. In that dense, energetic chaos, light was a prisoner. A photon, a particle of light, would try to travel but would immediately crash into a free electron, scattering in a new direction. It was a cosmic pinball machine, so thick and opaque that no beam of light could travel any meaningful distance. The universe was a glowing, impenetrable wall. Then expansion did its work. As space stretched, everything cooled. When the temperature finally dropped below about 3,000 degrees, something monumental happened. The free electrons, moving slowly enough now, were captured by protons. They combined to form the first stable atoms of neutral hydrogen. In that instant, the fog lifted. The free electrons that had been blocking the light's path were suddenly gone, locked safely inside atoms. The photons, after bouncing around for millennia, were finally set free. They began streaming unimpeded across the universe. That first flash of liberated light is what we see in the CMB. It is not a picture of the Big Bang itself, but of the moment the universe became transparent, the moment it turned the lights on for the very first time. Every single point in that ancient glow corresponds to a location where an atom formed and a photon began its endless journey. We are not just looking at light from the edge of the universe, we are looking at light from the edge of time. From the last moment, everything was everywhere at once. That first flash of light was almost unnervingly smooth. The temperature of that ancient sky from one patch to another is identical to, within a staggering precision, about 1 part in 100,000. If you painted the entire sky with that temperature, it would look like a single, uniform shade of deep, cold blue, a perfect cosmic canvas. This near-perfect uniformity is a profound clue. It tells us that in its earliest moments, the universe was in a state of incredible thermal equilibrium. Every region was in contact with every other, mixed together in that primordial soup. But here is the critical mystery. If the universe had been perfectly smooth, we would not exist. A perfectly uniform cosmos would have remained a featureless sea of hydrogen gas forever. There would be no clumps, no knots of gravity to gather matter. No stars, no planets, no galaxies, and certainly no us. The universe needed imperfections. It needed seeds, and the cosmic microwave background holds the blueprint for those seeds. Embedded within that near-perfect smoothness are the tiniest of ripples, minute variations in temperature. We call these anisotropies. In some spots, the ancient light is a few millionths of a degree warmer. In others, a few millionths of a degree cooler. These are not flaws in the picture. They are the fingerprints of creation itself. Those slightly warmer patches were ever so slightly denser, holding a tiny bit more matter. Over billions of years, gravity acted on those imperfections. It pulled the matter in the warmer, denser spots together, while the cooler, emptier regions became the vast cosmic voids we see today. Every galaxy supercluster, every spiral arm, every star in the night sky owes its existence to those microscopic wrinkles in the fabric of the newborn cosmos. The map of the universe we see today, with its great walls of galaxies and immense empty spaces, is simply those tiny temperature differences from the CMB, written large by 13.8 billion years of gravitational growth. We are the children of cosmic imperfection. The frustration felt by Penzias and Wilson was deeply human, a battle against a mystery that refused to yield. They had this magnificent, sensitive instrument, a horn antenna built for cutting-edge communications research, and it was plagued by a constant, low-level noise. This was not a dramatic burst of static, but a maddening, steady hiss that seemed to come from every corner of the sky, 24 hours a day. It was the scientific equivalent of a faint, untraceable hum in your house that you can never silence. Their first assumption was entirely reasonable: local interference. They carefully pointed the giant horn toward New York City, expecting the noise to spike from the radio chatter of millions of people. It did not change. They checked for radar reflections, for nuclear tests, even for signals bouncing off nearby satellites. Nothing explained it. Then they turned their suspicion inward to the antenna itself. Perhaps the instrument had a fault, a loose connection or an electronic flaw generating the noise internally. They found nothing. In a move that would become legendary, they focused on the most mundane of possibilities. Pigeons had taken up residence in the large, curved throat of the horn antenna. The scientists discovered a layer of what they diplomatically called white dielectric material coating the interior. They evicted the pigeons and with meticulous care scrubbed away every trace of the droppings, convinced this was the source of their trouble. Yet when they powered the antenna back on, the hiss remained utterly unchanged. That moment was a turning point from annoyance to profound curiosity. The signal was not from Earth, and it was not from their machine. It was coming from the universe itself. Their persistent nuisance was the oldest story ever told, waiting to be heard. This humble struggle against pigeon waste led directly to the confirmation of our universe's fiery birth, a reminder that the grandest truths are often hidden in the most stubborn details. That stubborn, universal hiss did more than solve a technical mystery. It settled one of the greatest scientific debates of the 20th century. For decades, cosmologists had been divided into two camps with radically different visions of cosmic origins. On one side was the Big Bang theory, which proposed the universe began in a state of immense heat and density and had been expanding and cooling ever since. It made a very specific prediction. If the universe was once that hot, the remnants of that initial fireball should still be around, cooled and stretched into a faint microwave glow that permeated all of space. On the other side was the rival steady-state theory. It argued the universe had no beginning and no end. It was eternal, and as it expanded, new matter was continuously created to keep its overall density constant. A universe with no explosive birth would have no relic heat, no background glow. The cosmic microwave background was the definitive test. When Penzias and Wilson, after their battle with the pigeons, finally published their findings, the implications were immediate and earth-shaking. They had found the precise signal the Big Bang model demanded and the steady-state model could not explain. This was not just supporting evidence, it was the smoking gun. The universe was not static and eternal, it had a dramatic, fiery beginning. That uniform microwave bath was the cooled-down ashes of the primordial inferno, the definitive proof we live in an evolving cosmos with a birthday. The discovery was so decisive it effectively ended the steady-state theory as a serious competitor. In one brilliant, accidental observation, the CMB transformed cosmology from a field of philosophical speculation into a rigorous historical science. We could now point to tangible evidence and say, this is what the universe was like in its first moments. That ancient flash of light has been on an unimaginable journey. When it first broke free from the primordial fog, it was not a faint microwave whisper. It was a brilliant, searing blaze. The photons of the cosmic microwave background began their existence as visible light and even higher energy ultraviolet radiation. glowing with the intense white-hot heat of a universe at about 3,000 degrees. If human eyes could have witnessed that moment, the entire sky would have been a uniform, blinding glare, like the surface of a star enveloping you in every direction. But then, the universe kept expanding, space itself stretched, and as it did, it pulled on the very fabric of that light. Imagine drawing a wave on a rubber band, then slowly stretching the band. The wave gets longer, its peaks farther apart. This is cosmological redshift. Over 13.8 billion years, the relentless expansion of the cosmos has stretched those initial waves of visible light by a factor of about 1,100. Their wavelengths grew from fractions of a millimeter to several centimeters, sliding down through the infrared and squarely into the microwave band. This is not a theoretical guess, it is a direct, measurable observation. The CMB is the most pristine and extreme example of redshift we have ever detected. Every time we point a radio telescope at that signal, we are not just looking back in time, we are witnessing the stretching of space-time itself, etched into the very color of the universe's first light. That cool microwave static is the direct and audible proof that space is dynamic, that it has grown, carrying the echoes of creation along with it. This perfect stretching left an unmistakable signature in the light itself, a fingerprint so precise it silenced any lingering doubts. The cosmic microwave background is not just any kind of radiation, it is a nearly perfect blackbody radiator. Now, that term sounds technical, but the concept is beautifully simple. A blackbody is a theoretical object that absorbs all radiation that hits it, and then re-emits that energy with a very specific, predictable pattern across different wavelengths. Think of a piece of iron in a blacksmith's forge. As it heats up, it first glows a dull red, then orange, then a brilliant yellow-white. The color and intensity of that glow at each temperature follows a precise mathematical curve, a unique thermal signature. The universe, in its first flash, behaved exactly like that piece of iron. The hot, dense plasma of the early cosmos absorbed and re-emitted light so efficiently that it achieved a state of perfect thermal equilibrium. When that light was finally set free, it carried the perfect blackbody spectrum of an object at about 3,000 degrees. Then, over billions of years, the expansion of space stretched that entire spectrum, cooling it down uniformly. The result is a cosmic glow that today matches the blackbody curve for an object at just 2.725 Kelvin with staggering fidelity. This is not a close match, it is a near-perfect overlap. For decades after its discovery, confirming this precise spectral shape was a holy grail for cosmologists. If the CMB's spectrum deviated even slightly from a perfect blackbody curve, it would imply something had interfered with the light during its long journey, perhaps injecting energy from unknown sources or processes. The universe itself was waiting to be graded on a curve. The answer came from a satellite named COBE, the Cosmic Background Explorer, launched by NASA in 1989. Its mission was to measure the CMB's spectrum with unprecedented accuracy. When the science team, led by John Mather, analyzed the data, the results were breathtaking. The points plotted from their instrument fell exactly on the theoretical blackbody curve. The match was so perfect, the error bars so tiny, that the graph looked like a single, smooth line with the data points lying directly on top of it. Scientists described it as seeing the fingerprint of God. This confirmation was monumental. It proved the early universe really was in that state of near-perfect thermal equilibrium, a simple, hot, dense soup. It ruled out a vast array of exotic alternative theories about the universe's youth. For this definitive measurement, proving the CMB was the cooled remnant of a primeval fireball, John Mather and the COBE team were awarded the Nobel Prize in Physics. That perfect curve is the universe's own birth certificate, signed in the language of thermodynamics and delivered across 13 billion years. Those microscopic wrinkles are more than just seeds for galaxies. They are a precise measuring tape for the shape of reality itself. The patterns of hot and cold spots in the cosmic microwave background, those tiny anisotropies, act as a cosmic ruler. Their specific size on the sky reveals the fundamental geometry of the entire universe. This is a profound idea. Geometry is not just about triangles in a textbook, it is the underlying fabric of space. General relativity tells us that mass and energy curve this fabric. The total amount of stuff in the universe, all the matter and energy combined, determines whether space is curved like a sphere, saddle-shaped like a horse's saddle, or perfectly flat. Each geometry has dramatic consequences. A closed, spherical universe would be finite, and parallel lines would eventually converge. An open, saddle-shaped universe would be infinite, with parallel lines diverging. A flat universe sits right on the knife edge between these two, where parallel lines stay parallel forever, and the total density is at a precise critical value. So, how do we measure the shape of something as vast as the cosmos? We use the CMB as a standard ruler. Those temperature fluctuations were imprinted when the universe was only 380,000 years old, and their physical size is determined by how far sound waves could travel in the primordial plasma before the light was set free. This gives us a known length, a fixed measuring stick etched into the ancient sky. Then we observe how big that ruler appears to us today. It is like holding a coin at arm's length. If the universe is positively curved like a sphere, space acts like a lens, bending light and making the coin appear larger. If the universe is negatively curved like a saddle, it would make the coin appear smaller. After decades of meticulous observation from satellites like WMAP and Planck, the answer is crystal clear. The coin appears exactly the size we expect it to be. The cosmic ruler in the CMB shows no magnification or minification. The universe on the largest scales we can measure is geometrically flat. This single measurement tells us that the combined density of all matter and energy in the cosmos is at that critical, precise value. It is a breathtakingly delicate balance, a cosmic tightrope walk that has held for billions of years, and its discovery was written in the subtle patterns of the universe's first light. Flat geometry demands a very specific cosmic recipe. The precise measurements of the cosmic microwave background do more than map the shape of space, they inventory its contents. By analyzing the subtle patterns of the ancient light, scientists have constructed a cosmic pie chart, a definitive breakdown of what the universe is actually made of. The results are both humbling and astonishing. Everything you have ever touched, seen, or loved, every star, planet, and galaxy, all the atoms forged in stellar furnaces, constitute a mere 5% of the total cosmos. This is ordinary matter, the protons, neutrons, and electrons that build the periodic table and form the world we know. It is the visible universe, and it is the overwhelming minority. The remaining 95% is composed of substances we cannot see, substances that do not interact with light at all. The first of these mysterious ingredients is dark matter, making up about 27% of the universe. We know it is there because of its immense gravitational pull, the way galaxies spin, the way they cluster together, and even the way the patterns in the CMB itself formed, all point to the existence of a vast, invisible scaffold of matter. Dark matter provides the gravitational glue that holds galaxies together, a cosmic skeleton around which the luminous stars and gas are draped. Without it, galaxies would simply fly apart. Yet, despite outweighing normal matter by more than 5-to-1, dark matter remains elusive, detectable only by the ghostly hand of its gravity. The final and most dominant slice of the pie is the most mysterious of all, dark energy. This enigmatic force accounts for a staggering 68% of the universe. Unlike matter, which pulls things together through gravity, dark energy is a repulsive force, causing the expansion of the universe to accelerate. It is the anti-gravity woven into the fabric of empty space itself. This three-part recipe, 5% atoms, 27% dark matter, and 68% dark energy, is not a speculative guess. It is the precise mixture required to produce the flat universe we observe, with the exact pattern of wrinkles we see in the cosmic microwave background. The CMB is the ultimate forensic tool, allowing us to deduce the composition of the entire cosmos from the faint imprint of its infancy. We live in a universe dominated by shadows, a place where the familiar world of atoms is just a thin shimmer on a deep, dark sea of the unknown. That perfect cosmic pie chart, however, comes with a disturbing footnote. As our maps of the cosmic microwave background grew more detailed, scientists began to notice something unsettling in the data. The universe, on its largest scales, appears to have a preferred direction, a strange alignment that whispers of a cosmic axis. This controversial feature has been dramatically nicknamed the axis of evil. The name itself tells you how troubling this finding is to our fundamental understanding. It challenges the cosmological principle, the cornerstone of modern cosmology, which states that, on large scales, the universe is homogeneous and isotropic. In plain language, it should look the same in every direction, with no special places and no preferred axis. There should be no up or down, no left or right to the cosmos itself. Yet, the axis of evil suggests there might be. This anomaly refers to an unexpected alignment of some of the largest patterns in the CMB. Certain warm spots and cool spots, the biggest ripples stretching across billions of light years, seem to line up along a particular plane in the sky, almost as if they are pointing in a common direction. It is as if you dropped a handful of pebbles into a perfectly still pond, and instead of seeing circular ripples expanding randomly, you saw them all subtly aligned along a single line. This should not happen in a universe born from a random quantum fluctuation and expanding uniformly. The statistical chance of such an alignment occurring randomly is incredibly small, which is why it demands an explanation. Some scientists argue it could be a subtle artifact of our own observation, a contamination from the glow of our own Milky Way galaxy that hasn't been fully subtracted from the data. Others wonder if it is a sign of something far more profound, a fossil imprint from the universe's first instance, a crack in the principle of universal sameness. Could the newborn cosmos have had a slight spin, or a fundamental asymmetry woven into its fabric from the very beginning? The axis of evil remains one of the most persistent and unexplained mysteries in the CMB, a ghost in the machine of cosmology that hints we may not yet understand the full rules of the game. The light from the cosmic dawn carries more than just temperature, it holds a hidden direction. The photons of the cosmic microwave background are polarized. This means the waves of this ancient light do not vibrate in every direction randomly. They have a subtle preference, a specific orientation imprinted upon them during their final moments of interaction with matter. Think of sunlight glinting off the surface of a lake. The light reflecting off the water becomes polarized, its waves aligning horizontally. The CMB experienced a similar scattering event on a cosmic scale just before it was set free forever. This polarization is an incredibly faint signal, buried within the already faint microwave glow, but it is a treasure trove of new information. Scientists categorize these polarization patterns into two distinct types, E modes and B modes, named for their mathematical resemblance to the patterns of electric and magnetic fields. E modes are the gentler, curling patterns. They are created by the same density fluctuations, the same hot and cold spots that we see in the temperature map. As the last photons scattered off the clumps of matter in the infant universe, their vibrations were twisted by the gravitational tug of those clumps, leaving behind this recognizable curl-like signature. Mapping the E modes gives us a second, independent view of the early cosmic structure, confirming the story told by the temperature map. But the true holy grail lies in the hunt for the other type, the B modes. These are a twisting, swirly pattern in the polarization, like the water swirling down a drain. E modes can be created by ordinary density variations, but B modes of a specific, large-scale kind could only be forged by something far more violent, the passage of primordial gravitational waves. These would be ripples in the very fabric of spacetime itself, generated in the first trillionth of a second after the Big Bang during a period called cosmic inflation, when the universe is thought to have expanded faster than the speed of light. Finding these specific B-mode patterns in the CMB would be direct observational evidence for inflation, offering us a glimpse into the universe when it was far younger than we can see with light alone. It would be like hearing the faint echo of the universe's first shudder, a vibration frozen into the polarization of its oldest light. The pursuit of this signal is one of the most intense and challenging quests in modern cosmology, a search for a whisper within a whisper that could rewrite our understanding of time's first moment. The hunt for those primordial B modes has become one of the most arduous and dramatic quests in modern science. This specific swirl in the ancient light's polarization is not just another feature, it is the direct signature of the universe's most violent and transformative moment. To find it would be to witness the instant of cosmic inflation. The theory of inflation proposes that in the first incomprehensibly tiny fraction of a second, the universe underwent a growth spurt of staggering proportions, expanding faster than the speed of light itself. This explosive stretching would have smoothed the cosmos to the near perfection we see, planted the seeds for all future structure, and most crucially, it would have shaken the very fabric of spacetime. That shaking would have generated gravitational waves, ripples in the geometry of reality. As these primordial waves passed through the hot plasma of the early universe, they would have left a unique, twisting imprint on the polarization of the CMB photons, creating those telltale B-mode patterns. Finding this pattern is the ultimate goal because it would provide direct observational proof of inflation, taking us from a compelling theory to a confirmed chapter in the history of everything. It would be like finding the fossilized footprint of the Big Bang's first explosive step. The most famous attempt to capture this ghostly signal unfolded at the South Pole. There, at one of the coldest, driest, and most stable observing sites on Earth, an experiment named BICEP, the background imaging of cosmic extragalactic polarization, scanned a pristine patch of sky for years. In 2014, the team made a stunning announcement. They had detected a B-mode signal and it was strong. The scientific world erupted with excitement. Headlines proclaimed the discovery of gravitational waves and evidence for inflation. It felt like a moment of historic triumph, but cosmic clues are rarely so straightforward. There was a formidable complication, one that exists right in our own galactic backyard: interstellar dust. Our Milky Way is filled with microscopic grains of dust, and this dust, when aligned by magnetic fields, can also emit polarized light that mimics the very B-mode signal scientists were desperate to find. It creates a foreground fog, a veil of galactic pollution that must be perfectly subtracted to see the pristine cosmic signal behind it. The initial BICEP results had relied on models to estimate this dust contamination. When the European Space Agency's Planck satellite, which had meticulously mapped this galactic dust across the entire sky, released its full data, the story changed. The B-mode signal BICEP saw was consistent with what could be produced by dust alone. The hoped-for discovery of primordial gravitational waves had been, at best, premature and at worst, a case of cosmic confusion. This episode was not a failure, but a masterclass in the rigorous, painstaking nature of cosmology. It highlighted the immense challenge of separating the universe's first whisper from the noisy chatter of our own galaxy. The search continues, with ever more sensitive instruments being built in the world's highest and driest deserts, all peering through the dusty veil, listening for the swirl that would tell us how it all began. Even the most pristine ancient light can be altered on its long journey to our telescopes. One of the most powerful ways we use the cosmic microwave background is not just as a picture of the past, but as a backlight to illuminate the present universe. This technique relies on a subtle interaction known as the Sunyaev-Zeldovich effect. Imagine the CMB as a uniform, cold screen of light shining from behind everything in the cosmos. Now picture a massive galaxy cluster, a city of thousands of galaxies held together by gravity. The space between those galaxies is not empty, it is filled with an incredibly hot, thin gas, so hot it glows in X-rays. As the ancient CMB photons travel for billions of years and finally pass through one of these clusters, they encounter this searing plasma. The hot, energetic electrons in the gas collide with the much colder CMB photons. In these collisions, the photons get a boost of energy, a kick, like a ping-pong ball being hit by a fast-moving paddle. This process, called inverse Compton scattering, changes the photon's properties in a specific and detectable way. It shifts some of the photons out of the microwave part of the spectrum and into slightly higher energies. When we look at that region of the sky, the CMB appears subtly distorted. In the direction of the galaxy cluster, the microwave background looks ever so slightly dimmer or colder at its characteristic frequency, while it appears brighter at higher frequencies. It is as if the cluster has cast a specific kind of shadow, a spectral fingerprint, onto the ancient light shining through it. This shadow is incredibly faint, but it has a revolutionary advantage: it does not get dimmer with distance. Whether a galaxy cluster is relatively nearby or at the edge of the observable universe, the Sunyaev-Zeldovich effect imprint it leaves on the CMB is the same strength. This makes it a perfect tool for cosmic archaeology, allowing astronomers to find and catalogue the most massive structures in the universe, even those so distant and faint they are invisible to optical telescopes. By scanning the microwave sky for these characteristic shadows, we are using the afterglow of the Big Bang as a universal searchlight, revealing the hidden architecture of the cosmos all around us. This universal backlight does more than reveal distant clusters, it reveals our own motion through the cosmos in the most direct way possible. The cosmic microwave background holds a secret about us, about our own place in the grand flow of galaxies. When scientists first mapped the temperature of the ancient sky with extreme precision, they discovered something that seemed to break its perfect uniformity. One half of the sky, centered roughly on the constellation Leo, is ever so slightly warmer than the opposite half. The difference is minuscule, only about 0.003 of a degree, but it is real and unmistakable. This pattern is called the dipole anisotropy, and it is not a flaw in the universe's design, but a signature of our own journey. The reason is a familiar effect known as the Doppler shift, the same phenomenon that makes a siren's pitch rise as it approaches you and fall as it moves away. We are moving at a tremendous speed relative to the rest frame of the CMB itself. As our solar system, along with our galaxy and its local group, travels through space, we are rushing headlong toward the region in Leo. The CMB photons coming from that direction are slightly compressed or blue-shifted by our motion. A blue shift means the light waves are squeezed together, which increases their energy and makes that patch of the ancient sky appear a fraction of a degree warmer. Conversely, the photons coming from the exact opposite direction in the sky are stretched out or redshifted by our motion away from that point. Their energy is decreased, making that half of the cosmos appear cooler. By carefully measuring the temperature difference across the entire sky, we can calculate our velocity with astonishing precision. The numbers are breathtaking. Our entire local group of galaxies is moving at roughly 630 kilometers per second relative to the CMB rest frame. But if we isolate just the motion of our solar system within the Milky Way, we find we are speeding toward Leo at about 370 kilometers per second. That is over 1.3 million kilometers per hour. We are not stationary observers of the universe, we are cosmic travelers on a high-speed voyage, and the oldest light in existence is the headlight and taillight that proves it. This dipole is our personal wake in the sea of relic radiation. a permanent reminder that even as we map the grand motions of the cosmos, we are participants in the flow. Our high-speed journey is measured against a silent backdrop, but the early universe was anything but quiet. It was a roaring, chaotic symphony of pressure and density, and the cosmic microwave background holds the sheet music. Those subtle temperature variations, the warm and cold spots we see as the seeds of galaxies, are not random static. They are the fossilized imprint of the universe's first sound waves, colossal pressure waves that race through the seething plasma like ripples across a cosmic pond. We call these primordial vibrations baryon acoustic oscillations. To understand this, picture the universe before it became transparent. It was a hot, dense fluid made mostly of photons, the particles of light, and baryons, which are the protons and neutrons that would later form atoms. These two components were tightly coupled, with the photons exerting an immense outward pressure. If a tiny region became slightly denser, gravity would try to pull the baryons inward, but the intense photon pressure would push them violently outward. This created a titanic tug of war. The result was a spherical sound wave, a shell of compressed matter and radiation that expanded outward from the initial overdensity at a significant fraction of the speed of light. For nearly 400,000 years, these pressure waves propagated through the cosmic fluid. Then, at the moment of recombination when atoms formed and the photons were set free, the music stopped abruptly. The waves froze in place, their final positions etched permanently into the sky. The CMB shows us that frozen moment. A hot spot in the ancient light often marks the center of one of these waves where the baryons finally gathered. Surrounding it, at a very specific distance, we see a subtle, cooler ring in the temperature map. That ring is the fossilized shell of the sound wave itself, the farthest point the pressure wave could travel before the universe fell silent. This characteristic scale, the distance a sound wave could travel in all that time, acts as a cosmic ruler stamped into the fabric of space. It is the universe's first and most fundamental note, a single, resonant frequency echoing from the dawn of time. That frozen symphony of sound waves reveals secrets about particles so ghostly they barely interact with matter at all. The cosmic microwave background acts as a cosmic census taker for the neutrino. Neutrinos are among the most elusive particles in existence, often called ghost particles because they can pass through light years of lead without a single interaction. Trillions of them are streaming through your body every second, remnants of the Big Bang and nuclear reactions in stars, and you feel absolutely nothing. In the first second of the universe, neutrinos were produced in staggering abundance, and like the photons, they decoupled from matter and have been streaming freely ever since. But unlike photons, which were trapped until the universe was 380,000 years old, neutrinos broke free when the cosmos was just 1 second old. This gave them a head start, and they began racing ahead of the slower, coupled plasma of photons and baryons. This early departure had a critical effect on those primordial sound waves. The gravitational influence of this sea of streaming neutrinos subtly changed how matter could clump together in the earliest moments. It smoothed things out just a bit, damping the formation of the very largest structures we see imprinted in the CMB. By analyzing the exact statistical patterns of the hot and cold spots, the precise distribution of their sizes, cosmologists can detect this damping effect. The data tells a clear story. It indicates that the total number of neutrino species or families that were light enough to be relativistic and streaming freely in the early universe is 3. Not 2, not 4, but 3. This is not a rough estimate. The exquisite precision of the Planck satellite data, combined with other cosmological observations, tightly constrains this number. It is a breathtaking convergence. In the world of particle physics, experiments conducted in giant underground detectors and powerful particle colliders had already concluded there are 3 families of light neutrinos. This conclusion came from smashing particles together at incredible speeds and studying the debris. Now, from the opposite end of the scientific spectrum, by studying the faint temperature variations in the afterglow of creation, cosmology arrives at the exact same number. The largest possible experiment, the universe itself, confirms the findings of the smallest. It is a profound reminder that the laws of physics are universal, governing the quantum foam and the cosmic horizon with the same unwavering consistency. The whisper of the Big Bang holds a census of ghosts, and it counts exactly 3. That cosmic whisper is not a steady tone, but a fading one. The temperature of the cosmic microwave background is not a fixed number for all eternity. It is a clock slowly ticking down. The 2.725 Kelvin we measure today is a snapshot in an endless process of cooling. This happens for the same fundamental reason the light exists in the first place, the relentless expansion of the universe. As space itself stretches, it stretches the wavelength of every single photon within the CMB. Think of drawing a wave on a balloon and then inflating it. The wave gets longer, its peaks farther apart. A longer wavelength of light carries less energy, and in the language of thermodynamics, lower energy means a lower temperature. The expansion is an irreversible cooler, constantly diluting the heat of the primordial fireball. The rate of cooling is incredibly slow by human standards, almost imperceptible over millennia, but it is inexorable. Billions of years from now, long after our sun has faded and the Milky Way has merged with its galactic neighbors, the CMB will be significantly colder. Its photons will have been stretched further into the lower energy radio band of the spectrum. Eventually, in a future so distant it defies comprehension, the cosmic microwave background will fade entirely from view. Its signal will become so faint, its wavelength so long, that it will slip below the threshold of anything our current technology could ever hope to detect. The universe's first light will dissolve into a near-perfect silence, a radio quiet so profound it would seem as if the echo of creation had never existed at all. This inevitable fading adds a poignant layer to our observations. We are living in a privileged cosmic era, a golden age for cosmology where this ancient afterglow is still bright enough for us to capture and decode. We are witnesses to a temporary phenomenon, catching the final, faint chapters of a story that is slowly closing its book. The subtle symphony of sound waves and ghost particles is not the only mystery written in the ancient light. Among the gentle statistical ripples of the cosmic microwave background, there are a few glaring outliers, places where the map of the infant universe seems to break its own rules. The most famous of these is known simply as the CMB cold spot. Discovered in 2003 by NASA WMAP satellite and later confirmed in exquisite detail by the Planck mission, this region of the sky is not just slightly cool, it is profoundly cold. It spans an area nearly 10 times the diameter of the full moon, and its temperature is about 70 microkelvin colder than the average surrounding background. That may sound tiny, but in the exquisitely uniform statistics of the CMB, it is a monstrous deviation, a statistical anomaly so large it should occur by random chance only about once in every 200 universes. So what could create such a bizarre feature in the universe's baby picture? The most straightforward explanation, and the one first pursued by astronomers, is that it is not a feature of the CMB itself, but something in the foreground. Perhaps a vast, nearly empty region of space, a cosmic supervoid, lies between us and that part of the ancient sky. As CMB photons pass through such a void on their way to us, they would climb out of its gravitational well, losing a tiny amount of energy in a process called the integrated Sachs-Wolf effect. This would make the light from that direction appear slightly cooler. It is a cosmic version of rolling a ball up a hill. It slows down. Astronomers have indeed found a large, underdense region of galaxies in that general direction, but the problem is one of scale. The supervoid they have identified, while immense, does not seem nearly large enough or empty enough to account for the staggering coldness of the spot. The numbers simply do not add up, leaving the cold spot colder than any conventional explanation can justify. This failure of the simple answer has opened the door to far more speculative and thrilling possibilities. Some theorists have proposed it could be the imprint of a cosmic texture, a defect in the structure of space-time itself left over from a phase transition in the very early universe, like a crack frozen into the fabric of reality. But the most mind-bending hypothesis of all suggests the cold spot might be evidence of a collision with another universe. In certain models of the multiverse, where our cosmos is one bubble in an infinite froth of expanding universes, such bubbles could occasionally brush against one another. The energy released in such a collision could leave a distinct circular bruise on our cosmic microwave background, a cooler region where the physics of our universe was subtly disturbed by the touch of another. While this remains a highly speculative idea, the very fact that scientists are willing to entertain it shows just how deeply perplexing this single, frigid patch of sky truly is. It is a ghost in the machine of cosmology, a place where the smooth story of our origins develops a crack, and through that crack we glimpse the possibility of realities beyond our own. The stubborn perfection of the cosmic microwave background has acted as a cosmic judge, dismissing entire families of alternative ideas about the universe. Its precise temperature, its near-perfect blackbody spectrum, and the specific pattern of its fluctuations together form a set of fingerprints so unique that they rule out contenders with ruthless efficiency. Take, for example, the once popular steady-state model. As we discussed, its prediction of no relic background radiation was decisively proven wrong by the mere existence of the CMB. But the story goes much deeper. Consider theories of a cyclic universe where the cosmos undergoes endless cycles of expansion, contraction, and rebirth in a big bounce. Many of these models struggle to explain the observed flatness and the specific statistical signature of the fluctuations we see. A universe that has been through multiple cycles would likely carry scars, imprints from previous epochs that would distort the CMB in ways we simply do not observe. The pristine, simple thermal state captured in that ancient light suggests a single, definitive beginning, not an endless replay. Similarly, ideas like plasma cosmology, which sought to explain large-scale structures without dark matter or a Big Bang, fail a critical test. They cannot reproduce the exquisite acoustic peaks in the CMB's power spectrum, those frozen sound waves we talked about. The precise spacing and height of those peaks are a direct reflection of the composition and geometry of the early universe, a composition that demands dark matter and dark energy to make the math work. Every detailed measurement of the CMB has tightened the noose around alternative models, forcing them to become increasingly contrived to fit the data. This relentless winnowing process is how science progresses. The cosmic microwave background is not just evidence for our standard model of cosmology, known as lambda CDM. It is the evidence that has systematically dismantled the competition. It has elevated lambda CDM from a plausible idea to the reigning champion, the only framework that consistently and elegantly explains the full suite of observations from the universe's first light to the large-scale structure we see today. The CMB is the ultimate arbiter, and its verdict is clear. The cold spot's mystery exists only because we have learned to see the cosmic microwave background with ever sharper eyes. Our understanding of this ancient light is not based on a single, blurry snapshot, but on a series of increasingly detailed portraits, each a technological masterpiece captured from the silent void of space. The first of these revolutionary missions was COBE, the Cosmic Background Explorer, launched by NASA in 1989. Before COBE, we knew the CMB existed and had a rough temperature, but its map of the sky was like a photograph taken with a severely out-of-focus lens. COBE gave us our first true full sky map, confirming with breathtaking certainty that the background radiation was a near-perfect blackbody, and for the first time revealing the faintest hint of those all-important temperature variations. Its instruments painted the sky in broad, gentle strokes, showing the cosmic dipole from our motion and the first whisper of the primordial lumps that would become galaxies. The map was coarse, with each pixel representing an enormous swath of sky, but it was the proof of concept that changed everything. It showed us the canvas upon which the universe's history was written. A decade later, the quest for detail intensified with the Wilkinson Microwave Anisotropy Probe, WMAP, launched in 2001. Where COBE saw a blurry impressionist painting, WMAP delivered a finely detailed sketch. Its resolution was over 30 times sharper, able to discern features less than 1 degree across. This was the mission that transformed cosmology from a speculative field into a precision science. WMAP exquisitely sensitive maps measured the temperature fluctuations with such accuracy that scientists could construct the universe's first detailed power spectrum, the cosmic musical score of those primordial sound waves. It pinned down the age of the universe to 13.7 billion years with a margin of error of just 1%, precisely measured the geometry as flat, and delivered the now standard cosmic recipe of 5% ordinary matter, 27% dark matter, and 68% dark energy. WMAP gave us the definitive low-resolution blueprint of cosmic infancy. The final and most breathtaking portrait came from the European Space Agency's Planck satellite, which observed from 2009 to 2013. If WMAP was a detailed sketch, Planck's map is a high-definition photograph of stunning clarity. Its resolution is over 3 times finer than WMAP, and it measured the temperature of the CMB with a sensitivity of a few millionths of a degree. Looking at a Planck map compared to COBE is like comparing a modern satellite image of Earth to a hand-drawn map from the age of exploration. Every subtle contour, every intricate ripple in the ancient plasma is laid bare. Planck measured the polarization of the light, hunted relentlessly for the elusive B modes, and constrained the properties of dark matter and neutrinos with unprecedented rigor. It confirmed the standard model of cosmology with overwhelming confidence while simultaneously highlighting the anomalies, like the cold spot and the axis of evil, that now taunt us from the data. These 3 missions, COBE, WMAP, and Planck, represent a ladder of discovery. Each step upward provided a clearer view of our cosmic origins, turning a faint hiss of static into the most important story ever told, written in the temperature of the sky itself. Planck's final map is a testament to the power of patient, silent observation. From its vantage point a million miles from Earth, the European Space Agency's Planck satellite spent 4 years, from 2009 to 2013, doing one thing with obsessive perfection: listening to the cosmic microwave background with ears more sensitive than anything ever built. Its mission was to capture the ultimate portrait of the universe's infancy, and it succeeded beyond all expectation. Where its predecessor, WMAP, gave us a detailed sketch, Planck delivered a photograph in ultra-high definition. Its resolution was so sharp it could discern features in the ancient sky just a few arc minutes across, finer than the apparent size of a dime held at arm's length. This was not merely a sharper picture, it was a deeper one. Planck's instruments were so exquisitely sensitive they could measure temperature variations in the CMB down to a few millionths of a degree. To achieve this, the satellite's detectors had to be cooled to a fraction of a degree above absolute zero, making them among the coldest objects in the universe, colder even than the background radiation they were studying. This incredible precision was not for show, it was the key to unlocking the universe's most tightly held secrets. Every subtle contour in that map, every minute variation in temperature and polarization, held encoded information about the cosmos's composition, age, and birth. Planck's data refined every single cosmological parameter to a razor's edge. It pinned down the age of the universe at 13.8 billion years with astonishing certainty. It measured the universe's expansion rate, the Hubble constant, with a precision that would later reveal a troubling tension with other methods. Most importantly, it placed the tightest constraints ever on the models of cosmic inflation. The theory of inflation predicts a specific pattern for those primordial quantum fluctuations, a statistical fingerprint. Planck measured that fingerprint with such fidelity that it ruled out whole classes of inflationary models. Simple, elegant versions of the theory survived, while more complex, Baroque ideas were shown to be incompatible with the pristine data. Planck did not discover inflation, but it told us which versions of that explosive beginning are still plausible and which are not. Its legacy is one of definitive refinement, turning the broad brushstrokes of cosmology into a pointillist masterpiece of precision, where every tiny dot of data tells a part of the grandest story. Planck's breathtaking portrait of cosmic infancy is not the end of the story, but a gateway to an even more ancient past. The cosmic microwave background, while a photograph from 380,000 years old, is actually a palimpsest, a document with older writing visible beneath the surface. Its patterns, the specific arrangement of those hot and cold spots, hold encoded information from a time vastly more remote, from the first trillionth of a second after the Big Bang. This is the epoch of cosmic inflation, a period when the universe is thought to have expanded exponentially faster than the speed of light. We cannot see that moment directly. No light from that time could possibly reach us, but its violent tremors left an indelible mark on everything that followed. Think of it like this. Imagine shaking a bowl of gelatin. After you stop shaking, the gelatin will continue to jiggle for a while, its surface covered in ripples that slowly settle. Now freeze the gelatin at the exact moment the jiggling is most pronounced. The frozen surface does not show your hand that did the shaking, but the pattern of ripples is a direct record of that initial violent motion. The CMB is that frozen surface. The inflationary epoch was the hand that gave the universe its fundamental shake. During that unimaginably brief instant, quantum fluctuations, tiny random variations in energy that exist even in a vacuum, were stretched from microscopic to cosmic size by the explosive expansion. These stretched quantum seeds became the primordial density fluctuations, the slight overdensities and underdensities that would later, through gravity, grow into galaxies and clusters. The specific statistical signature of these fluctuations, their size, their distribution, their gentle Gaussian randomness, is precisely what we read in the temperature map of the CMB. By analyzing the intricate details of that map, we are not just looking at a 380,000-year-old universe. We are inferring the physics of a reality that existed for less time than it takes light to cross a single proton. The whisper from the cosmic dawn carries the echo of creation's first and most violent heartbeat. That frozen ripple pattern, a direct imprint from inflation, defines the very shell of our observable universe. This leads us to a powerful and slightly mind-bending idea, the last scattering surface. This is not a physical wall out in space, not a giant crystal sphere enclosing the cosmos. It is a moment in time made visible in every direction we look, 13.8 billion years ago, in every single point of the space that would become our entire observable universe. Atoms formed and light was set free. Those photons began streaming outward in all directions. The ones that happened to be heading toward the spot that would one day become Earth have been traveling toward us ever since, for the entire age of the cosmos. Now, after their 13.8 billion-year journey, they are finally arriving at our telescopes all at once. We are at the center of a vast spherical shell of light, a shell that marks the moment the universe became transparent. The radius of that shell is not a distance in space as we normally think of it. It is a distance in time, 13.8 billion light-years. Every photon hitting our detectors right now, from every point in that microwave sky, left the edge of that sphere at the same instant when the universe was a mere infant. So when we map the cosmic microwave background, we are not looking at different objects at different distances. We are looking at a single, universal event, the moment of last scattering, painted across the entire dome of the sky. It is the ultimate celestial sphere, a photograph of a single moment of cosmic childhood, with us at the center, receiving the news 13.8 billion years late. We are surrounded by a fossilized instant. The patterns in that ancient light are a silent witness to a universe dominated by shadows. The specific distribution of hot and cold spots in the cosmic microwave background, the precise statistics of those primordial seeds, could not have grown into the cosmic web we see today without an immense, invisible helping hand. That hand belongs to dark matter. The story told by the CMB is one of gravity sculpting the cosmos, but the math only works if there is far more gravity than the visible atoms can provide. Remember, the ordinary matter we see, the protons and neutrons called baryons, were tightly coupled to the intense radiation pressure of the photons in the early universe. This coupling created a powerful outward push that resisted gravity's attempt to clump matter together. Baryons alone, under that relentless photon pressure, could not have collapsed into the dense knots needed to form galaxies within the age of the universe. The seeds were there in the CMB, but they needed a stronger, quieter force to nurture them. This is where cold dark matter enters the narrative. Unlike baryons, dark matter does not interact with light or radiation. It is immune to that searing photon pressure. From the very first moments, dark matter particles could begin to clump together under their own gravity, unaffected by the cosmic wind. They formed a vast, invisible scaffolding in the darkness, wells of gravitational potential long before the universe became transparent. When the ordinary matter finally broke free from the radiation at the moment of last scattering, it had a ready-made blueprint to follow. The baryons simply fell into the gravitational pits already dug by the dark matter. This head start is absolutely critical. Without it, the gentle ripples in the CMB would have remained just that, gentle ripples, never amplifying into the magnificent galaxies and clusters that fill our night sky. The cosmic microwave background and the large-scale structure of the modern universe are 2 pages of the same story, and dark matter is the plot device that connects them. The CMB tells us the initial conditions, and the galaxy surveys show us the final result. The only way to get from that smooth, infant universe to our clumpy, structured cosmos is with a massive amount of matter that feels gravity but not light. The whisper from the cosmic dawn does not just hint at dark matter, it demands its existence, quantifying exactly how much of this mysterious substance must be woven into the fabric of reality for our universe to make sense. This invisible scaffolding of dark matter solves one cosmic mystery but immediately reveals another, far stranger one. The cosmic microwave background does more than demand dark matter. It sets the stage for the universe's most dominant and perplexing actor, dark energy. The story begins with that flat geometry, the critical cosmic balance sheet we measured from the CMB's patterns. The total density of the universe must equal a precise value to make space flat. Our inventory from the CMB tells us exactly how much of that density comes from matter, both ordinary and dark. It accounts for about 32% of the total required for flatness. So here is the glaring question: what makes up the other 68%? For decades, this missing majority was a gap in the equation, a placeholder. Then, in the late 1990s, observations of distant supernova delivered a shocking answer. Astronomers found that these exploding stars, used as cosmic mile markers, were fainter than expected. The universe was not just expanding, its expansion was accelerating. Something was pushing galaxies apart with ever-increasing force. That something was given a name: dark energy. The CMB provided the crucial context for this discovery. By itself, the accelerating expansion was astonishing, but when combined with the CMB's precise measurement of flatness and matter density, it became undeniable. The geometry said the universe must be flat. The matter inventory said we only have about a third of the needed stuff. The supernova said expansion is speeding up. Only one component could tie all these threads together, a form of energy inherent to space itself that exerts a repulsive gravity. Dark energy fills that 68% gap perfectly, satisfying the flatness condition while simultaneously driving the acceleration. The CMB did not discover dark energy directly, but it corralled it. By tightly constraining the amount of matter, it left no hiding place for this mysterious force. The ancient light told us exactly how much room was left on the cosmic balance sheet, and dark energy rushed in to claim it. We now live in a universe whose fate is dictated not by the gravity of matter, but by the repulsive push of this enigmatic energy, a conclusion forced upon us by the cold, hard numbers written in the universe's first light. That repulsive push of dark energy is quantified by a single, critical number, the Hubble constant. It is the current expansion rate of the universe, the speed at which galaxies are receding from us for each megaparsec of distance. Pinpointing this number is one of the most important goals in cosmology, as it tells us how fast the universe is growing and allows us to calculate its age and fate. For decades, scientists have pursued two primary, independent paths to measure it. One path looks at the nearby universe using brilliant stellar explosions called Type Ia supernova and pulsating stars known as Cepheid variables as cosmic mile markers. By measuring their distance and how fast they are moving away, astronomers can calculate the Hubble constant directly. The other path looks to the ancient universe using the cosmic microwave background as its guide. The detailed pattern of fluctuations in the CMB encodes the universe's expansion history. By plugging the standard model of cosmology into the CMB data, scientists can extrapolate forward in time to predict what the Hubble constant should be today. These are two completely different methods, one a direct measurement of the present and the other a deduction from the deep past. They should agree, they do not. This is the Hubble tension, and it is a full-blown crisis in modern cosmology. The CMB method, using the exquisitely precise data from the Planck satellite, predicts a Hubble constant of about 67.4 kilometers per second per megaparsec. The local measurements, refined over years by teams using the Hubble Space Telescope and other observatories, consistently find a higher value, around 73 kilometers per second per megaparsec. The gap is small, only about 9%, but the precision of each measurement is so high that the chance this is a simple error is vanishingly small. We are not talking about a minor discrepancy, we are talking about two of the most robust pillars of modern astronomy stubbornly disagreeing. This is not a case of one being right and the other wrong. It is a signal that our standard model of the universe, the lambda-CDM model that has been so successful, might be incomplete. The whisper from the cosmic dawn and the shout from today's galaxies are telling us two different stories about how fast space is stretching. One possibility is that there is something we do not understand about the supernova or Cepheids, some hidden systematic error in the local measurements. Yet, as teams have checked and rechecked their work, the local value has only become more firm. The other, far more thrilling possibility is that the CMB is revealing a crack in our physics. Perhaps dark energy is not constant but has evolved over time, changing its repulsive strength in a way our models do not account for. Maybe there is an unknown type of neutrino or another exotic particle that influenced the early universe's expansion in a way that changes the CMB's prediction. Or perhaps our understanding of gravity itself needs revision on the largest scales. The Hubble tension is not a problem to be solved, it is a clue. It is the universe telling us that the story we have pieced together from its first light is missing a crucial chapter, a piece of physics that operates in the vast, dark gulf between the infant cosmos and the universe we see today. This disagreement between the past and the present may be our best guide to discovering what lies beyond our current map of reality. The Hubble tension forces us to question everything we think we know, but some theories go even further, challenging the very idea of a single beginning. The cosmic microwave background might not just be a relic of our universe's birth, but a scar from a death that came before. This is the radical proposal of conformal cyclic cosmology, a theory developed by the Nobel laureate physicist Roger Penrose. In this breathtaking vision, our universe is not the first and only one. It is merely the latest in an endless cycle of cosmic eons, each beginning with its own Big Bang and ending when all matter has evaporated into radiation through the decay of black holes. The transition between these eons is not a violent collision, but a graceful mathematical transformation. As one eon ends, expanding into an infinite, empty, timeless state, its geometry can be conformally rescaled, meaning its scales are mathematically remapped to become the hot, dense, energetic beginning of the next. In this model, the Big Bang is not a singularity from nothing, but a continuation, a rebirth. But if a previous universe existed, could we possibly find evidence of it? Penrose believes we already have, and that the evidence is written in the concentric rings of the cosmic microwave background. His claim centers on an audacious idea that information can survive the transition between eons. Specifically, the titanic collisions of supermassive black holes from the previous eon would have sent out immense bursts of gravitational waves. These waves, ripples in spacetime itself, would have imprinted concentric circular patterns onto the fabric of that dying universe. According to Penrose's mathematics, those ghostly circles could have carried through the conformal rescaling at the Big Bang and been subtly stamped onto the CMB of our current eon as faint rings of slightly lower temperature variation. They would be like the faint, water-stained patterns from a previous page showing through on a new sheet of paper. Penrose and his colleagues have analyzed the WMAP and Planck data, announcing they have found precisely these kinds of concentric ring structures, which they call Hawking points, in honor of Stephen Hawking's work on black hole evaporation. These are not the familiar hot and cold spots of primordial sound waves, but larger, more subtle circular anomalies in the temperature map. If confirmed, these rings would be echoes of the most cataclysmic events from a cosmos that existed before time as we know it began. The physics community remains deeply skeptical. Many scientists argue that the patterns Penrose identifies are consistent with the random statistical fluctuations we would expect to see in any complex dataset, the cosmic equivalent of seeing faces in clouds. The standard inflationary model provides such a powerful explanation for the CMB structure that adding a previous eon seems unnecessary to most cosmologists. Yet, the sheer boldness of the idea captivates the imagination. It suggests our entire cosmos, with its billions of galaxies and trillions of stars, might one day dissolve into a silent sea of radiation, only to provide the raw material for a new fiery beginning. The cosmic microwave background, then, would be more than a baby picture. It would be an inheritance, a palimpsest containing the final, fading signature of a universe that lived, died, and gave birth to our own. The faint whisper of the CMB is a laboratory for the most profound physics imaginable. Those initial microscopic ripples, the very seeds of all galaxies, were born from the quantum realm. In the first fleeting moments of inflation, the universe was so incredibly small that quantum mechanics ruled its behavior. Empty space itself was not truly empty, but a seething foam of virtual particles flickering in and out of existence, creating tiny, random fluctuations in energy. Then, inflation acted like a cosmic magnifying glass. It stretched these quantum jitters from a scale smaller than a proton to a scale larger than a galaxy cluster, freezing them into the fabric of spacetime as the primordial density variations we now see in the CMB. This means the majestic cosmic web, with its billions of galaxies, originated as subatomic tremors. When we study the statistical pattern of the hot and cold spots in the ancient light, we are not just doing astronomy. We are reading a fossilized quantum mechanical record, a snapshot of the universe when it was governed by the bizarre rules of the very small. This connection offers a rare and precious opportunity. Quantum mechanics describes the behavior of particles and forces on the smallest scales with stunning accuracy. General relativity describes gravity and the geometry of the cosmos on the largest scales with equal brilliance. Yet, for a century, these two foundational pillars of physics have refused to be united into a single, coherent theory of quantum gravity. The problem is one of access. We cannot build a particle accelerator large enough to recreate the energies where gravity becomes a quantum force, but the early universe was that accelerator. The CMB provides the data from that impossible experiment. By scrutinizing the ultra-fine details of its fluctuation patterns, scientists are looking for subtle anomalies, tiny deviations from the predictions of standard inflation that could be the signature of quantum gravity effects. Did spacetime itself have a granular quantum texture at the beginning? Could that texture have left a specific statistical fingerprint on the way those primordial ripples were laid down? These are not just philosophical questions. The cosmic microwave background is the only observational window we have into that epoch where gravity and quantum mechanics were inseparable. It is our one chance to test ideas about the fundamental nature of reality against the hard data of the cosmos itself. The echo of creation is not just a relic, it is a message from a domain where the rules of physics as we know them were being written. That perfect blackbody curve is a masterpiece of cosmic simplicity, but the universe is never truly static. Even after that first flash of light was set free, its journey was not over. The pristine spectrum we measure today, that fingerprint of perfect thermal equilibrium, might one day reveal faint scars from events that occurred long after the cosmic dawn. This leads us to a thrilling prediction for the future of cosmology. Upcoming generations of experiments with sensitivities far beyond anything we have now may detect minuscule deviations from that perfect blackbody shape. Scientists call these anomalies spectral distortions. Imagine the cosmic microwave background as a perfectly smooth, pure musical note. A spectral distortion would be a barely audible harmonic, a slight warble in the tone, introduced because something touched the light during its 13 billion-year voyage. These distortions would not come from the universe's birth, but from its adolescence and even its maturity. What could possibly alter the sacred light of creation? One tantalizing possibility involves the ghosts of the early universe, ancient particles left over from the Big Bang. Certain theoretical particles, like actions or other weakly interacting massive particles, might slowly decay over cosmic time. As they decay, they would inject tiny amounts of energy into the intergalactic medium, subtly heating the electrons in the vast voids between galaxies. When a cold CMB photon passes through a region where this has happened, it could get a tiny kick from these warmer electrons, shifting its energy ever so slightly. Over billions of light years, these minute interactions could collectively warp the perfect blackbody spectrum into a new, distorted shape. Each type of decaying particle would create a unique spectral fingerprint, meaning we could potentially identify the specific particle that caused it, turning the CMB into a cosmic particle detector spanning the entire observable universe. Another profound source of spectral distortion could be the evaporation of primordial black holes. These are not the black holes formed from dying stars, but hypothetical micro-black holes that could have been forged in the insane densities of the universe's first second. According to Stephen Hawking's famous theory, black holes slowly evaporate, radiating away their mass. For a primordial black hole nearing the end of its life, this evaporation would be a violent burst of energy and particles. If a significant population of these tiny black holes evaporated en masse at a certain cosmic epoch, they would have flooded the universe with a fog of radiation and heat. This energy injection would have interacted with the CMB photons, leaving a specific, calculable distortion in the spectrum. Finding that distortion would be direct proof that these exotic objects, relics of the universe's most extreme conditions, truly existed. The hunt for these spectral distortions is a search for the universe's lost energy. It is the next frontier in CMB science, moving beyond the snapshot of infancy to read the diary of everything that happened afterward. Our current satellites, as magnificent as they are not quite sensitive enough to see these whispers, but missions now being planned with detectors cooled to even more extreme temperatures and shielded with unprecedented care are being designed with this exact goal. They will listen not just for the note of creation, but for the faint, telling echoes of everything that followed. But even that perfect blackbody curve and its intricate small scale patterns hint at a deeper, large-scale mystery. The cosmic microwave background exhibits a surprising quietness on its grandest scales, a smoothness that defies our expectations. This is known as the low quadrupole problem, and it is another persistent whisper that something in our cosmic story might be missing. To understand it, think of the sky as a globe like the Earth. The temperature fluctuations in the CMB can be broken down into components, much like you can describe the Earth's surface with terms like its average temperature, its north-south temperature gradient, and more complex patterns. The quadrupole moment refers to the specific pattern of hot and cold that spans 1/4 of the entire sky. It is one of the very largest possible ripples in the cosmic fabric. According to our standard model of cosmology, which is built upon the physics of inflation and quantum seeds, the universe should have a certain expected amount of power, a certain level of temperature variation on these colossal scales. The models make a clear prediction for how strong this quadrupole signal should be. Yet, when we look at the actual data from WMAP and Planck, the quadrupole is significantly weaker than predicted. The biggest patches of the sky are more uniform, more eerily similar to each other than our best theories say they should be. It is as if the universe's first symphony is missing its deepest, most resonant bass note. This is not just a minor statistical fluke. The probability of this happening by random chance in our standard model is less than 1 in a few hundred. So what could suppress these largest of all ripples? One possibility is that the universe is simply not as big as we think it is. If the entire cosmos is finite and smaller than the observable horizon, then the very largest waves simply would not fit inside it, like trying to fit an ocean swell into a swimming pool. The CMB patterns would hit a wall, a cosmic cutoff, explaining the lack of power on the biggest scales. Another, more subtle idea involves the shape of space itself. While we know the universe is flat on average, it could have a more complex topology, like a video game screen where if you go off one edge you reappear on the other. Certain finite, multiply-connected shapes could also naturally filter out these ultra-long wavelength fluctuations. Or perhaps the answer lies in the very beginning with inflation itself. Maybe the inflationary period did not last quite as long as our simplest models assume, cutting off the growth of those primordial quantum fluctuations before they could stretch to truly universe-spanning sizes. Each of these explanations would force a profound revision of our cosmic history. The low quadrupole, together with the axis of evil and the cold spot, forms a trio of large-scale anomalies that refuse to be ignored. They are the quiet corners of the cosmic baby picture, the places where the expected chaos of birth gives way to an unexpected and still unexplained calm. This cosmic quiet on the largest scales makes the subtle warping of its small details all the more critical. The ancient light does not travel to us in perfectly straight lines. Its journey is a winding path, bent and twisted by the gravity of everything it passes. This phenomenon is gravitational lensing, and the cosmic microwave background is its ultimate canvas. As those 13-billion-year-old photons stream toward us, they pass by massive galaxy clusters, vast clouds of dark matter, and every other concentration of mass in the late universe. According to Einstein's theory of general relativity, mass curves the fabric of space-time. Light must follow these curves so its path is deflected, much like a glass lens bends light to focus it. The effect on a single photon is infinitesimal, but across the entire sky, with trillions of photons passing by trillions of massive objects, the collective distortion becomes measurable. It does not create new hot or cold spots in the CMB. Instead, it subtly rearranges the existing ones, stretching and squeezing the pattern of the primordial sky. It is as if you were looking at a printed photograph of the infant universe, and then someone placed a series of faint, warped magnifying glasses over certain parts of the image, slightly smearing the ink. This lensing effect is incredibly faint, a distortion of only about 1 part in 10,000, but with the exquisitely detailed maps from Planck and other experiments, scientists have learned to see it. They use sophisticated statistical tools to analyze the CMB's texture, looking for telltale correlations between temperature points that should be unrelated. These correlations reveal how the ancient pattern has been sheared and magnified by the gravity of all the matter that has formed in the billions of years since the light began its voyage. The result is not just a temperature map of the early universe, but a lensing map of the entire cosmic web. This map is revolutionary because it traces all matter, both the luminous galaxies we can see and the vast, invisible scaffolding of dark matter. By charting these subtle gravitational deflections, we create a three-dimensional mass map of the cosmos, showing where all the stuff is, seen and unseen. It is the universe using its own oldest light to take an X-ray of its present-day skeleton, revealing the hidden architecture that guides the growth of everything. This subtle warping of light is not the only way the universe's later growth leaves a mark on its first light. As the cosmic microwave background photons travel for billions of years, they climb in and out of the gravitational hills and valleys carved by the cosmic web. Most of the time, if these gravitational landscapes were static, the energy a photon loses falling into a valley would be perfectly regained as it climbs out the other side. The net effect would be zero, but our universe is not static, it is expanding, and dark energy is causing that expansion to accelerate. This changes everything. The vast gravitational potentials, the deep wells of galaxy clusters, and the broad hills of cosmic voids are themselves evolving, slowly weakening as the universe stretches. When a CMB photon enters a growing cluster, it loses energy falling in, making it appear slightly cooler. But if that cluster's gravitational well has shallowed by the time the photon climbs out, it regains less energy than it lost. The photon emerges with a net energy deficit, appearing ever so slightly colder than the surrounding sky. Conversely, a photon passing through a large, growing void experiences the opposite. It gains energy entering the underdensity, but as the void deepens, the photon loses more energy climbing out than it gained, resulting in a net blue shift, a slight warming. This phenomenon is the integrated Sachs-Wolf effect, a direct imprint of the changing gravitational landscape across cosmic time. It is an incredibly subtle signal, a secondary ripple on top of the primordial temperature map, but it is a direct fingerprint of the universe's dynamic expansion. Crucially, in a universe without dark energy, where matter dominates and gravitational potentials remain strong, this effect would be virtually non-existent. The fact that we can detect it at all, through precise statistical correlations between the CMB and maps of nearby galaxies, is another independent line of evidence for dark energy's repulsive push. It tells us that the cosmic structures are losing their gravitational grip, their wells shallowing as the fabric of space itself stretches them apart. The integrated Sachs-Wolf effect turns the ancient light into a sensor for the changing gravity of the cosmos, allowing us to feel the slow, relentless fade of the universe's largest structures under the influence of its most mysterious force. Magnetic fields are woven into the fabric of our modern cosmos. They guide star formation, shape the spiral arms of galaxies, and thread the vast voids between them. But where did these immense, invisible forces come from? The cosmic microwave background may hold the secret. potentially revealing that magnetism is not a latecomer to the universe, but a fundamental feature written into its first moments. Scientists are now hunting for the ghostly imprint of primordial magnetic fields within the ancient light's polarization. These would not be the fields generated later by swirling gas in galaxies or exploding stars. These would be relics from a time before the first atoms, fields generated in the unimaginable chaos of the universe's birth, perhaps during inflation itself or in the violent phase transitions that followed. If such fields existed, they would have left a distinct twisting signature on the CMB photons as they scattered for the last time. The hot, magnetized plasma of the infant universe would have caused the light to polarize in a specific curl-like pattern, similar to the B modes created by gravitational waves, but with a different statistical fingerprint. Finding this signature would be a discovery of staggering importance. It would mean magnetism is as primordial as space and time, a basic ingredient baked into the recipe of creation. It would transform our understanding of cosmic evolution, suggesting these ancient fields provided the seeds for all the magnetic structures we see today, gently guiding the first clumps of matter and influencing the formation of the very first stars and galaxies. The search is phenomenally difficult as the signal is incredibly faint and easily confused with the polarization from interstellar dust within our own Milky Way. Yet the possibility alone reshapes our view of the early universe. It was not just a smooth, hot soup of particles, but potentially a turbulent, magnetized plasma, crackling with invisible forces that helped sculpt everything that followed. The universe's first light holds a clue to its most fundamental imbalance. We exist because matter won a decisive, ancient victory. For every particle of matter, theory says there should be an identical twin of antimatter with opposite charge. When matter and antimatter meet, they annihilate in a flash of pure energy. If the Big Bang had created equal amounts of both, the entire universe should have self-destructed in a blinding instant, leaving behind nothing but a fading sea of radiation. Yet here we are, surrounded by galaxies, stars, and planets made of matter. This means that in the universe's first moments, for every 10 billion antimatter particles, there were 10 billion and 1 matter particles. That 1 in 10 billion asymmetry is the reason anything at all survived the annihilation. It is the reason we are here. The cosmic microwave background provides a crucial piece of this puzzle, not by showing us the asymmetry directly, but by telling us the exact scale of the victory. The number of protons and neutrons, the baryons, left over after that great annihilation is imprinted in the very sound waves we see frozen in the CMB. The relative heights of those acoustic peaks, the specific pattern of the hot and cold spots, is exquisitely sensitive to the density of ordinary matter in the early universe. From this, we can count the survivors. The CMB tells us that baryons make up about 5% of the cosmic density, a precise census of the matter that won the war. This number is the target, the answer that any theory of baryogenesis, the creation of more matter than antimatter, must explain. It is the universe's ledger sheet showing the final balance after the primordial conflagration. The conditions needed to create this imbalance are extreme, requiring a universe that was out of thermal equilibrium, where both matter-antimatter symmetry and charge parity symmetry were violated. These conditions are thought to have existed only in the first sliver of a second after the Big Bang, at energies far beyond any particle collider we could ever build. So we look to the cosmos as our laboratory. Certain models of baryogenesis predict not just the number of baryons, but also other subtle effects that could have left a faint trace on the cosmic microwave background. Some theories suggest that the forces responsible created not just more matter, but also primordial magnetic fields or specific types of gravitational waves. As we have seen, the hunt for the twisting B-mode polarization in the CMB is a search for those gravitational waves, which could be a direct signal from the epoch when matter's fate was decided. Other models might leave an imprint on the way matter is distributed on the largest scales, a signature that could be teased out by comparing the CMB's ancient map with the structure of the modern universe. The whisper from the cosmic dawn is the final outcome statement of that first and most critical battle. By reading its details with ever greater care, we are searching for the echoes of the physics that tipped the scales, that chose existence over perfect, silent symmetry. The whisper of the CMB is a time capsule for particles that have never been seen. The cosmic microwave background does more than map photons. It holds an indirect census of the universe's most ghostly inhabitants, the relic neutrinos from the Big Bang. These are not the neutrinos streaming from our sun or distant supernova today. These are the ancient ones created in the first second of the cosmos, when the universe was so hot and dense that even these aloof particles were constantly interacting. As the universe expanded and cooled roughly 1 second after the Big Bang, neutrinos decoupled from the rest of the cosmic soup. They stopped colliding with other particles and began streaming freely through the expanding universe, forming a cosmic neutrino background. This sea of ghost particles is all around us, trillions passing through your body every second, but they are so fantastically difficult to detect that we have never captured a single one from this primordial source. Their energy is now so low that current technology simply cannot sense them. Yet we know they are there, and we know their precise influence because the cosmic microwave background felt their presence profoundly. Before the CMB was emitted, when the universe was a seething plasma, these relic neutrinos were a dominant component. They made up a significant fraction of the universe's total energy density, and they moved at nearly the speed of light. This matters because the expansion rate of the early universe is governed by what fills it. The presence of this fast-moving, or relativistic, neutrino sea altered how quickly space stretched in those critical moments before the CMB photons broke free. A faster expansion rate changes the physics of the primordial sound waves. Specifically, it dampens the formation of the very largest ripples in the plasma. Think of trying to create a standing wave in a pool of water. If you start draining the pool too quickly, the largest, slowest waves never have time to fully form before the water level drops. The relativistic neutrinos acted like that accelerated drain, subtly suppressing the power of the largest scale fluctuations in the infant cosmos. This damping leaves a specific, calculable fingerprint on the statistical pattern of hot and cold spots we see in the CMB's power spectrum. By analyzing that pattern with exquisite care, cosmologists can measure the damping effect and work backwards. They can deduce not only that these relic neutrinos existed, but also how many different types or flavors there were and what their combined mass might be. The data tells us the number of light neutrino species is 3, perfectly matching discoveries from particle colliders here on Earth. It also tells us that the combined mass of all 3 neutrino types is incredibly small, a fact that has profound implications for particle physics. So while we cannot yet trap these ancient ghosts in a laboratory, the CMB serves as our ultimate neutrino detector. It recorded their gravitational influence on the cosmos's infancy, preserving a snapshot of their role in shaping the universe's expansion history. The oldest light we see carries the shadow of the universe's first ghosts, a permanent record of particles that otherwise slip through our fingers and our detectors without a trace. That census of ghost particles and the precise geometry of the cosmos place extraordinary demands on any theory of everything. The cosmic microwave background has become a ruthless arbiter, not just for cosmology, but for the most ambitious frameworks in theoretical physics, including string theory. String theory proposes that the fundamental constituents of reality are not point-like particles, but tiny, vibrating strings. The different vibrational patterns of these strings give rise to all the particles and forces we observe. It is an elegant, mathematically beautiful idea that promises to unify gravity with quantum mechanics. but it comes with a staggering consequence, a prediction of extra dimensions of space, curled up so small we cannot perceive them. The specific way these dimensions are compactified leads to an almost inconceivable number of possible universes, each with different physical laws and constants. This is the famous string theory landscape, a vast cosmic library containing perhaps 10 to the 500 different possible versions of reality. Our universe, with its specific particle masses and force strengths, would be just one book on one shelf in this infinite library. For decades, this landscape seemed like a theoretical playground with no way to test which book, if any, described our home. Then came the exquisitely precise data from the cosmic microwave background. The CMB provides a set of numbers that any successful theory of the early universe must reproduce. One of the most telling is the spectral index, labeled as NS. This is not a measure of color, but of the texture of the primordial fluctuations. It tells us how the size of those initial quantum seeds varied with scale. A perfectly scale invariant spectrum, where ripples of all sizes were equally likely, would have a spectral index of exactly 1. But inflation predicts a slight deviation, a gentle tilt where smaller ripples are a tiny bit more common than larger ones. The actual measurement from the Planck satellite pins this number down with incredible precision. NS equals 0.965. This is not just any number, it is a specific fingerprint of how inflation unfolded, the rate at which the universe expanded during that explosive moment. This single, precise decimal point acts like a cosmic bouncer at the door of the string theory landscape. It immediately disqualifies entire wings of the library. Many possible compactifications of the extra dimensions, many versions of inflation derived from string theory, predict a spectral index that falls outside the incredibly tight error bars set by the CMB data. They are simply incompatible with the universe we observe. This is not a failure of string theory, but a powerful demonstration of how empirical data can tame theoretical speculation. The CMB forces string theorists to look for models that naturally produce a slow-roll inflation ending with a spectral index very close to 0.965. It guides the search, telling physicists where in the vast landscape they should focus their efforts. The whisper from the cosmic dawn is thus a message to the most advanced theoretical minds, a set of boundary conditions written in the sky that any viable theory of quantum gravity must ultimately obey. Our universe is not just any possibility, it is one with a very specific, measurable beginning, and that beginning holds the key to unlocking the fundamental nature of reality itself. The shape of space itself might be far stranger than an infinite flat sheet. The cosmic microwave background could be our key to discovering if the universe has a hidden, finite geometry, a cosmic topology that would fundamentally redefine our place within everything. We have measured the universe's geometry to be flat, but that does not necessarily mean it is infinite. A flat piece of paper can be rolled into a cylinder, its edges joined together. In 3 dimensions, a flat universe could be wrapped into shapes like a 3 torus, a kind of giant, multidimensional donut where if you travel far enough in one direction, you return to your starting point from the opposite side. This is a multiply-connected space, a finite universe with no boundary. If our cosmos had such a shape, it would leave a ghostly fingerprint in the ancient light. Because space would wrap around on itself, the light from a single, massive object like a galaxy cluster could take multiple paths to reach us. We might see the same cluster appearing in 2 or more different places in the sky, like a cosmic hall of mirrors. More subtly, the vast ripples in the cosmic microwave background, those primordial sound waves, would also wrap around. This would create specific, unexpected correlations in the temperature map, patterns of matching circles or repeating statistical signatures on opposite sides of the sky. It would be as if the universe's baby picture were a wallpaper with a repeating pattern, a subtle clue that space is finite and connected. For decades, cosmologists have hunted for these telltale signs in the data from WMAP and Planck. They have searched for matching circles of temperature fluctuation, for statistical echoes that betray a closed geometry. So far, they have found nothing convincing. The CMB appears consistent with a simply connected, flat universe that extends forever. The simplest interpretation is that we live in an infinite, unbounded cosmos. Yet, the search is not over. The absence of evidence is not proof. If the universe is very large, even if finite, the repeating patterns might be on scales larger than our observable horizon, hiding just beyond the edge of the light we can see. Or perhaps the topology is so complex that its signature is too faint for our current instruments to discern. The possibility remains a tantalizing whisper at the edge of cosmology. To discover that the universe is finite, that all of existence could, in principle, be mapped and catalogued, would be a philosophical revolution. It would mean that everything, from the greatest galaxy supercluster to the smallest particle, exists within a comprehensible, if unimaginably vast, container. The cosmic microwave background is the one map detailed enough to possibly show us the seams. The universe's oldest light must first pass through the bustling neighborhood of our own galaxy, and this creates a formidable problem of cosmic pollution. To see the pristine cosmic microwave background, the baby picture of the universe, astronomers must first peel away a brilliant, swirling veil of emission from the Milky Way. Our galaxy is not a quiet, dark window into the beyond. It is a vibrant and noisy foreground, glowing brightly in the very same microwave frequencies we use to study the ancient cosmos. This foreground comes from three primary sources, each a distinct form of local interference. First, there is interstellar dust. Tiny grains of silicate and carbon, smaller than a wavelength of light, are scattered throughout the galactic plane. These grains are warmed by starlight and re-radiate that energy in the far infrared and microwave bands, creating a diffuse, hazy glow that obscures the CMB. Second, there is synchrotron radiation. This is the light emitted by high-energy electrons spiraling at nearly the speed of light along the Milky Way's tangled magnetic fields. It is a non-thermal, whirling glow that permeates the galaxy, particularly strong in the bustling center and along the spiral arms. Third, there is free emission, sometimes called Bremsstrahlung. This occurs when free electrons in the hot, ionized gas of the galaxy are accelerated as they pass near atomic nuclei, shedding energy as a smooth, broad spectrum of radiation. Together, these three emissions create a brilliant, complex tapestry of microwave light that is often thousands of times brighter than the faint whisper of the CMB itself. Imagine trying to listen to a faint, distant symphony while standing next to a roaring waterfall, a revving motorcycle, and a crackling bonfire all at once. The challenge is not merely that the foreground is loud, but that its composition changes dramatically across the sky and varies with frequency. The dust emission is strongest at higher microwave frequencies, while synchrotron radiation dominates at lower frequencies. To solve this, scientists deploy a strategy of multi-frequency observation. Satellites like Planck did not just look at the sky in one microwave color. They observed it in 9 separate frequency bands from 30 GHz to 957 GHz. Each band sees a different mixture of the CMB and the galactic foregrounds. By comparing these maps with exquisite precision, sophisticated algorithms can identify the unique spectral signature of each component, the dust, the synchrotron, the free emission, and finally, the pristine blackbody curve of the cosmic microwave background. It is a monumental exercise in cosmic subtraction, a data analysis challenge of staggering complexity. A single mistake, a slight misestimation of the dust's properties or the synchrotron spectrum, can leave artificial ripples or erase real ones in the final CMB map, potentially creating false anomalies or hiding true ones. The incredible maps we see from Planck and WMAP, those clean portraits of the infant universe, are not raw photographs. They are masterpieces of statistical cleaning, the result of peeling back the vibrant skin of our own galaxy to reveal the ancient fossilized light beneath. This painstaking process reminds us that we are not detached observers of the cosmos. We are embedded within it, and our view of the ultimate beginning is always filtered through the dynamic, living galaxy we call home. This absolute reference point transforms how we measure the cosmos. Because we understand the physics of the cosmic microwave background with such profound precision, it has become the ultimate standard candle for the universe. In astronomy, a standard candle is an object with a known intrinsic brightness. By comparing how bright it appears from Earth to how bright we know it truly is, we can calculate its distance and thus map the scale of the cosmos. For centuries, astronomers relied on objects like Cepheid variable stars or Type Ia supernova for this purpose. But each of these has limitations, chains of calibration that stretch back through space, each link introducing potential error. The CMB cuts through all of that. It is not just one candle in the darkness, it is the entire backdrop against which every other light is seen. Its properties, its temperature, and the specific angular size of the sound wave imprints are not assumptions. They are direct, measurable features of the universe itself, derived from fundamental physics. This gives us a fixed, universal ruler. We know, for instance, the actual physical size of those frozen sound waves at the moment the CMB was emitted. Then, by measuring how large they appear to us on the sky today, we can perform a simple geometric calculation to determine the distance to the last scattering surface, the edge of the observable universe. It is the most fundamental triangulation possible, using the universe's own birthmarks as the scale. This makes the CMB the bedrock upon which the entire cosmic distance ladder is built. Every other measurement, from the distance to nearby galaxies to the expansion rate of the universe, is ultimately checked and calibrated against this ancient, unwavering glow. It is the cosmic equivalent of the platinum iridium bar that once defined the meter in a Paris vault, but this bar is 13.8 billion light-years long and etched into the fabric of spacetime. When we say a galaxy is a certain number of megaparsecs away, that number is meaningful only because it can be traced back, step by step, to the immutable reference of the cosmic microwave background. It is the anchor that keeps our map of the universe from drifting into speculation. That absolute reference point, however, comes with a profound and humbling limitation. We have only one universe to observe. The cosmic microwave background we map with such exquisite care is a single, unique sky, the only baby picture of our cosmos that will ever exist. This means we cannot run the experiment of creation again and again to see if the patterns change. We cannot compare our universe's CMB to that of another cosmos born under slightly different conditions. We have one dataset, one snapshot of the initial conditions, and from that alone we must deduce the laws that govern everything. This fundamental constraint forces cosmologists to think in a very specific way. They cannot rely on the details of any individual hot or cold spot, no matter how strange it may seem. A single anomalous cold region, like the one we discussed, might be a fascinating statistical fluke, a cosmic roll of the dice that just happened in our particular universe. It is not, by itself, proof of a collision with another reality or a cosmic texture. To separate true physics from random chance, scientists must analyze the collective behavior of all the fluctuations. They do this by translating the temperature map into a powerful statistical tool called the power spectrum. Imagine the CMB sky as a complex musical chord. The power spectrum is not the melody itself, but a graph showing the volume or power of each individual note that makes up that chord. It breaks down the map into its constituent waves, plotting how much temperature variation exists on different angular scales, from the vast swaths of sky down to the finest details our telescopes can resolve. This graph is the true testing ground for theories. The standard model of cosmology, with its ingredients of dark matter, dark energy, and inflation, makes a very specific prediction for the shape of this power spectrum. It forecasts a series of peaks and troughs at particular scales, the harmonic signature of those primordial sound waves. The breathtaking agreement between this prediction and the actual data from Planck is what gives the model its immense credibility. When cosmologists debate the meaning of an anomaly like the axis of evil, they are not arguing about the visual alignment of a few spots on a map. They are performing rigorous statistical tests on the power spectrum, asking whether the data shows a preferred direction in a way that exceeds what random chance in a single universe should allow. This statistical lens is our only way to see past the quirks of our particular cosmic birthplace and glimpse the underlying laws that would govern any universe. We are detectives with a single, magnificent crime scene, forced to use the mathematics of probability to reconstruct the events of creation. The patterns we cherish are not a blueprint but a single outcome, and from that one roll of the cosmic dice, we must infer the design of the dice themselves. That single roll of the cosmic dice has already determined our final destination. The parameters we read from the cosmic microwave background, the flat geometry, and the overwhelming dominance of dark energy are not just a description of the universe's past, they are a prophecy for its future. The fate of everything is written into those ancient temperature fluctuations. A flat universe with a positive cosmological constant, our best model for dark energy, points toward a specific and profoundly lonely end. This ultimate destiny is often called the Big Freeze or heat death. It is not a dramatic explosion or a violent collapse, but a slow, inexorable fade into darkness and cold. Because dark energy's repulsive force is constant, or may even grow stronger, the expansion of the universe will continue to accelerate forever. Distant galaxies we see today will, over billions of years, recede faster and faster until their light can no longer reach us. They will not vanish in a puff of smoke, but will simply slip beyond our cosmic horizon, one by one, like ships disappearing over the curve of the ocean. The sky will grow emptier. Eventually, our local group of galaxies, bound together by gravity, will be all that remains visible, an isolated island in an ever-darkening sea of nothingness. Within that island, stars will continue to burn for trillions of years, but even they will eventually exhaust their fuel. New star formation will cease as the raw materials are locked away in dead stellar remnants, white dwarfs, neutron stars, and black holes. Over timescales that make the current age of the universe seem like a blink, even these remnants will decay. Protons themselves, the building blocks of all normal matter, may not be stable forever. Some theories suggest they will slowly decay over staggering eons. If that happens, every atom in every frozen, dead star and planet will gradually evaporate into a faint mist of radiation and subatomic particles. The universe will become a nearly perfect vacuum, colder than the current CMB, stretched so thin that any remaining particles are separated by distances greater than the size of our observable universe today. In this final state, no work can be done, no structure can form, no heat can flow from a hotter place to a colder one, because everything will be at the same infinitesimal temperature. It will be the ultimate equilibrium, a state of maximum entropy where the story of the cosmos reaches its final, silent page. This is the heat death, the inevitable thermodynamic conclusion dictated by the numbers we pulled from the whisper of the cosmic microwave background. We are not headed for a fiery crunch or a cyclical rebirth, according to this data, but for an eternal, quiet, and cold dispersion. The universe's first light, that warm echo of a hot beginning, points directly to this frigid end. That profound, cold end is written in a signal you might have touched as a child. The cosmic microwave background is not locked away in distant space. It is literally in the air around you, and for generations people have seen it without ever knowing. If you are old enough to remember analog television, you might have witnessed the echo of creation. When you tuned a television set to a channel with no broadcast signal, the screen would fill with a chaotic dance of black and white static. That snow, that hissing crackle, was not pure electronic noise. Roughly 1% of that flickering chaos came directly from the cosmic microwave background. Those tiny, dancing specks of light and dark were, in part, the ancient photons from the universe's first moments, captured by your television antenna after a 13.8 billion-year journey. Your living room was a portal to the dawn of time. The television antenna was acting as a crude radio telescope, picking up microwave radiation from across the cosmos. Most of the static came from terrestrial sources, from our own atmosphere, and from the synchrotron glow of the Milky Way. But a small, vital fraction was that universal hiss, the cooled remnant of the Big Bang itself, transformed into a visual spectacle of dancing grains on a cathode ray tube. It is a beautiful and humbling thought that one of the most important discoveries in human history was hiding in plain sight, disguised as a mundane annoyance, a thing to be tuned out while waiting for your favorite show to begin. Today, with digital signals, that window has closed. Our modern screens display a blank blue screen or a polite message when there is no signal. A cleaner, quieter experience that has inadvertently severed a direct tactile connection to the cosmos. We traded a glimpse of the universe's birth for a tidier picture, yet the signal is still there, waiting for anyone with the curiosity and the right gear to find it. Dedicated amateur radio astronomers have taken up the challenge, with homemade horn antennas similar in principle to the one used by Pensier's and Wilson, sensitive radio receivers, and a great deal of patience. They can detect the cosmic microwave background from their backyards. They are not mapping its intricate fluctuations that requires the cryogenic precision of a space satellite, but they can measure its overwhelming presence, that steady microwave bath that fills the sky. The process involves meticulous calibration, careful shielding from local interference, and long hours of pointing their equipment at the cold, empty spaces between stars. For these enthusiasts, the reward is profound. It is the moment when, after subtracting all the known sources of noise, a persistent signal remains, a signal that does not come from Earth or the Sun or even our galaxy. It is the whisper of the universe itself, captured not by a multi-billion-dollar space agency, but by ingenuity and passion. This accessibility is a testament to the CMB's omnipresence. It is not a distant object to be studied, it is the very medium we live within. From Nobel Prize-winning scientists to a curious person in their garden shed, the same ancient light is there for anyone willing to listen, a direct line from our humble planet to the very origin of everything. The universe's first light may be the wall of our own cosmic room. The detailed patterns in the cosmic microwave background provide our strongest evidence for the theory of cosmic inflation, that explosive faster-than-light expansion in the first fraction of a second. But inflation as a physical process may not have been a one-time event. Many models suggest that once inflation starts, it is eternal. In this breathtaking picture, the vacuum of space possesses a kind of latent energy that can cause random patches to suddenly and violently inflate, spawning new, separate universes like bubbles forming in an endlessly boiling pot. Our entire cosmos, with its hundreds of billions of galaxies, would be just one of these bubbles, one region where inflation happened to stop, allowing for the hot Big Bang and the formation of stars and planets. The rest of the megaverse, the greater inflating background, continues to expand eternally, giving birth to an infinite number of other bubble universes, each with potentially different physical laws and constants. Where does the cosmic microwave background fit into this staggering idea? It would be the inner surface of our bubble. Think of our observable universe as the interior of a vast, expanding sphere. The last scattering surface, the source of the CMB, is not the edge of existence, but the cooled, fossilized boundary of our local region where inflation ended and our familiar physics began. The near-perfect uniformity we see across the sky is exactly what you would expect from a smooth, energetic wall that was once connected, a single quantum event that stretched into our entire cosmic horizon. The tiny fluctuations, those quantum seeds, are the microscopic imperfections on that bubble wall magnified to a cosmic scale. This framework transforms how we view the CMB. It is no longer just a relic of our beginning, but a literal map of the interior of our local cosmic bubble, a bubble floating in an infinite, frothing sea of other realities. While we cannot see other bubbles, their existence is a natural, and some would say inevitable, consequence of the same physics that gave us the pristine, flat, and structured universe we observe in the ancient light. The whisper we have been decoding is not the voice of all creation, but the echo from our own chamber in a cathedral of universes beyond number. The smooth bubble of our universe might have cracks in its foundation. Within the elegant framework of cosmic inflation, physicists speculate that the rapid phase transitions of the early cosmos could have left behind not just quantum seeds, but actual topological defects, tears in the fabric of spacetime itself. One of the most famous of these theoretical relics is the cosmic string. Imagine a flaw in a crystal, a line where the atomic structure doesn't align perfectly, creating a persistent line of tension. A cosmic string would be like that, but for the universe itself, it would be an unimaginably thin, incredibly dense filament of pure energy, a crack in reality left over from when the fundamental forces of nature froze into their current forms. A single cosmic string, thinner than a proton, could stretch across the entire observable universe, and its mass would be so immense that a kilometer of it could outweigh Mount Everest. These are not strings in the sense of string theory, but rather cosmic scars, one-dimensional wrinkles that time forgot to smooth out. If they exist, they would have drifted through the cosmos for billions of years, and their ghostly presence would have left a unique and haunting signature in the oldest light we see. As the cosmic microwave background photons streamed past these ultra-dense filaments, the immense gravity of the strings would have acted like a cosmic lens, but with a bizarre twist. A moving cosmic string would create a step-like discontinuity in the temperature of the CMB, a sharp line across the sky where one side is slightly hotter than the other. But an even more distinctive fingerprint would be etched into the light's polarization. The gravitational shear from a string would not just bend the light, it would twist it. This would create a distinctive vortex-like pattern in the polarization map, a swirling, pinwheel signature centered on the string's location. It would look like a whirlpool in the sea of ancient light, a clear sign that something with immense linear gravity had passed through. This polarization vortex is a holy grail for cosmologists hunting for these exotic relics. Finding one would be a direct window into the universe's first moments, confirming that the early cosmos underwent dramatic phase transitions and left behind tangible scars. It would be evidence of a cosmic history more textured and complex than our smoothest models suggest. Current telescopes, for all their precision, have not yet seen this telltale swirl. The signal is incredibly faint, and it requires mapping the CMB's polarization with even greater sensitivity and resolution than we have achieved so far. But the next generation of observatories, like the Simons Observatory in Chile and potentially future space missions, are being designed with this exact goal in mind. They will scan the microwave sky with millions of detectors, searching for those ghostly whirlpools in the polarization, the frozen eddies left by strings that may have dissolved eons ago or may still be drifting through the dark, silent and unseen, waiting to reveal themselves in the twist of the universe's first light. That faint static from the cosmic dawn is more than an astronomical curiosity. It is a universal translator. The cosmic microwave background functions as a Rosetta Stone for physics, a single, magnificent data set that allows us to decipher the fundamental laws of reality across disciplines that are often studied in isolation. This ancient light bridges the chasm between the unimaginably small and the incomprehensibly large, weaving together the stories told by particle physics, general relativity, quantum mechanics, and thermodynamics into one coherent narrative. It is the one experiment where all these forces played out together, and we have the results. From particle physics, the CMB gives us a precise count of the neutrino families and constrains the properties of hypothetical particles like actions or WMAP, the weakly interacting massive particles that could be dark matter. The universe's expansion history, etched into the light's patterns, is a direct test of general relativity on the grandest possible scale, confirming that gravity shapes the cosmos as Einstein predicted. The initial seeds of all structure are quantum mechanical fluctuations, microscopic probabilities inflated to cosmic size, making the CMB a fossilized record of quantum behavior. And the perfect blackbody spectrum is a masterpiece of thermodynamics, a snapshot of a universe in near-perfect thermal equilibrium. No laboratory on Earth could ever recreate the conditions that naturally united these four pillars of physics. We cannot build a collider that spans light years, nor a vacuum chamber the size of the observable universe. Yet the cosmos performed this experiment for us in its first fleeting moments. By reading the subtle hieroglyphics of temperature and polarization in the CMB, we are doing more than cosmology. We are conducting fundamental physics. Each precise measurement, each constraint on a particle's mass or a theory's parameter, is a line translated from the language of the cosmos into the language of our textbooks. This makes the whisper of creation our most profound interdisciplinary tool, a message that reminds us the universe does not respect the boundaries we draw between fields of study. It is all connected, and the proof is written in the cool, ancient light that fills the void. Our current maps of the ancient sky are masterpieces, but they are not the final word. The next generation of cosmic cartographers is already assembling, building instruments of such staggering sensitivity they will listen to the universe's first light with entirely new ears. Ground-based projects like the Simons Observatory in Chile's Atacama Desert and the proposed, even more ambitious CMBS-4 represent a colossal leap forward. Their goal is not just to take a better picture, but to perform a forensic analysis of the cosmic microwave background's most subtle feature, its polarization. Imagine moving from a standard television to an ultra-high-definition screen that also reveals the hidden magnetic fields and stress patterns within the image itself. These observatories will deploy arrays of tens of thousands of superconducting detectors working in unison across multiple frequencies. This army of sensors will map the polarization of the CMB with a precision and resolution we can barely conceive of today. Their primary quarry remains the Holy Grail, the primordial B-mode polarization from inflationary gravitational waves. With orders of magnitude more sensitivity, they will either find that swirling signature definitively, confirming our story of inflation's violent shudder, or they will place such tight constraints on the theory that cosmologists will have to fundamentally rethink the universe's first instant. But the ambition goes far beyond B-modes. This exquisite new data will act as an ultra-fine sieve, capable of catching particles and phenomena that slip through our current nets. It could reveal the spectral distortions from decaying dark matter, the unique polarization swirls left by cosmic strings, or subtle statistical anomalies pointing to new forces or particles that interacted with the cosmos in its youth. These are not just telescopes, they are time machines tuned to the first trillionth of a second, and their findings will either cement our current cosmic narrative or force us to write a completely new one from the first page. The cosmic microwave background is our primary messenger, but it is not the universe's only echo. The first 380,000 years were preceded by even earlier epochs, and they too left behind their own relic signals, fossilized backgrounds that permeate all of space. There is a cosmic neutrino background, a sea of ghost particles that decoupled from matter just 1 second after the Big Bang. These ancient neutrinos are everywhere, trillions passing through you each second, but their energy is so low that catching one is a feat beyond our current technology. Then there is the background of primordial gravitational waves, the ripples in space-time from inflation itself. These waves would still be vibrating through the cosmos today, a faint hum beneath the silence. We hunt for their signature in the CMB's polarization, as we discussed, but they also constitute their own independent background of space-time vibrations. In the far future, there may even be a background of gravitational waves from the mergers of supermassive black holes across cosmic history, a chorus of low-frequency rumbles. Yet, for all these theoretical echoes, the cosmic microwave background stands alone in its clarity and accessibility. It is the only one we have mapped, the only one we can point to and say, this is the picture. The neutrino background is a ghost we infer from its gravitational influence. The gravitational wave backgrounds are whispers we strain to hear, but the CMB is a shout, a detailed, full-sky photograph that arrived ready for us to develop. It remains the singular, primary text from the universe's infancy, the one chapter we can read with our eyes wide open, while the others remain written in ink that has yet to become visible. That universal whisper is more than data. It is a direct connection to the moment of our own genesis. Every photon of the cosmic microwave background that strikes a telescope's sensor today is a 13.8 billion-year-old messenger. It has traveled across the entire span of cosmic history, completely untouched, to deliver a single, pristine piece of information. It left its source when the universe was a mere infant, a hot plasma of pure potential, and it has journeyed through the expanding dark ever since, never colliding with another atom, never being absorbed and re-emitted by a star. Its path has been bent by gravity and its wavelength stretched by the expansion of space. But the information it carries about that first moment of freedom remains uncorrupted. These photons are the ultimate time capsules. They are not a story told by an intermediary or recorded in some cosmic fossil record. They are the event itself, arriving in real time just 13.8 billion years later. When we detect them, we are not interpreting ancient history. We are receiving a signal that has been in transit since before our planet, our sun, or even the Milky Way galaxy existed. We are catching the universe in the act of telling its own origin story, and we are the first beings, at least that we know of, positioned and intelligent enough to understand it. To study the CMB is to engage in the most profound form of cosmic archaeology. We are not digging through layers of sedimentary rock. We are sifting through layers of time itself, using light as our trowel. Each subtle variation in temperature, each specific pattern of polarization, is a clue placed there in the first instant, waiting patiently through the rise and fall of stars, the birth and death of galaxies, for a curious mind to finally decipher it. This connection is deeply humbling. The same physical processes that forged hydrogen and helium in that primordial fireball are the ones that later, inside generations of stars, forged the carbon in our bones, the oxygen in our lungs, and the iron in our blood. We are not separate from the cosmos we observe, we are its direct product. The story the CMB tells is ultimately our own origin story. The photons bathing our detectors today are the very same ones that once filled the entire universe with a blinding light, and now, after an almost endless journey, they complete their voyage by interacting with a civilization built from the ashes of stars that would not exist without the seeds those photons helped to plant. We are the universe awakening to contemplate its own beginning, using the oldest light in existence as its mirror. The story of the cosmic microwave background is not a closed book, its final chapter already written. This is the final and perhaps most important thing to know. We are still learning from it. That ancient whisper is not a solved puzzle, but a living dialogue between the cosmos and our curiosity. Every time we build a more sensitive instrument, every time we stare at that map with sharper eyes, we peel back another layer, revealing not just answers but deeper, more profound questions. The journey from that first frustrating hiss in New Jersey to the exquisitely detailed Planck map was not a march toward a finish line, but an expansion of the territory we know we must explore. Each new level of precision has been a revelation, and with each revelation, new anomalies have emerged from the data like shapes forming in the mist. The cold spot, the axis of evil, the stubborn Hubble tension, these are not failures of our models, but their greatest success. They are the places where the universe is pointing a finger, saying, "Look closer, there is something here you do not yet understand." These anomalies are the cracks where the light of new physics might shine through. They hint at forces or particles beyond our standard model, at a dynamic dark energy, or at a fundamental reshaping of our concepts of space and time. The CMB is the ultimate calibration tool for reality itself, and right now it is telling us our calibration is slightly off. This ensures that this fossilized light will remain the engine of discovery for decades, perhaps centuries to come. The next generation of observatories, with their armies of superconducting detectors, will listen to its polarization with such fidelity that they might finally hear the swirl of primordial gravitational waves or catch the spectral distortion of a decaying dark matter particle. They will either confirm our grand story of inflation or force us to tear it up and start anew. The cosmic microwave background is a gift that keeps on giving, a message from the beginning that is still being decoded. Its final lesson is one of boundless humility and excitement. The universe's first story is not yet fully told, and we are only just beginning to learn how to read. That journey from a frustrating hiss to a cosmic cornerstone reveals a profound truth about science itself. It began with two astronomers, a giant antenna, and a battle against pigeon droppings, a story so wonderfully human. Their stubborn pursuit of a simple technical annoyance cracked open the universe's deepest history. That persistent noise was not a flaw in their machine, but the cooled echo of the Big Bang, a whisper that had traveled for over 13 billion years to reach a quiet field in New Jersey. From that single, accidental discovery, we have built an entire science. The cosmic microwave background is now the bedrock of modern cosmology, our single most powerful tool for understanding everything. It is the photograph that shows us the universe's infancy, the ledger that inventories its shadowy contents of dark matter and dark energy, and the prophecy that foretells its distant, cold fate. It is a laboratory for quantum gravity, a detector for ghostly neutrinos, and a ruler for the shape of reality. Every time we point a telescope at that ancient light, we are not just looking back, we are reading the ultimate origin story, our own. So the next time you see static on an old television screen or in the crackle between radio stations, pause for a moment. Remember that within that noise lies the faintest echo of creation, a story written in microwaves that began before time itself had meaning. We have decoded 50 astonishing secrets from that whisper today, but which one amazed you the most? Was it the universe's perfect temperature, the ghostly sea of neutrinos, or the chilling prophecy of the Big Freeze? Let us know in the comments below. If you are captivated by these deep mysteries of space, be sure to subscribe. We are just beginning to learn how to read the cosmos, and there are countless more wonders waiting.